Hello, I'm Jack. Welcome to my channel, Practical Programming with Dr. Su. In this video series, you will learn everything you need to get started with wgpu graphics programming in Rust. In the last few videos, we discussed how to use the color map model to build a 3D simple surface. In this video, I will explain how to create 3D parametric surfaces with lighting and color map effects. As shown previously, the key feature for a 3D simple surface is that for each x and z value pair, it can have at most one y value. However, sometimes you may want to create a complex 3D surface of a certain shape. This kind of surface cannot be represented by a simple mathematical formula. For certain values of x and z, this type of surfaces can have more than one y values. This means that we cannot use the approach discussed in the last few videos to store and display the data. One way to represent such a surface is to use a set of parametric equations that define the x, y, and z coordinates or point on the surface in terms of the parametric variables u and v. As shown here, you can see this is a parametric surface can be described by these equations: x equal to x uv, y equal to y uv, and z equal to z uv. Here, u and v are parametric variables. Many complex surfaces can be represented using these parametric equations, such as the sphere, torus, clean bottle, and so on. In fact, the simple surface is just a special case of the parametric surface. Here we can easily convert a simple surface into a parametric surface using this formula here. Suppose we have original have y equal to fxz. This is a simple 3D surface. If we set x equal to u and z equal to v, and y will equal to f, u, and v. This way we can convert a simple 3D surface into a parametric 3D surface. Use these formulas. Note that in the parametric space, for each u and v value pair, the function is single valued. This means in the parametric space, our parametric surface is a simple surface. So we can use the approach for the simple surface to create the parametric surface in the parametric space. This way, we can still use the quadrilateral masquerade in the UV space to approximate the parametric surface, as shown here. This quadrilateral unit cell contains the four vertices P0, P1, P2, and P3. This will be the same as we use in creating a simple 3D surface. But here, right now, we define the quadrilateral unit cell in the UV space. One problem with the approach in creating the simple 3D surface is that we calculate the normal vector for this quadrilateral unit cell. That is, all the vertices have the same normal vector. This means that each unit cell has a different lighting effect. As shown here, you can see these clear boundaries among each unit cell. You can see this one unit cell and another. So this gives a not very smooth transition from one unit cell to another. So you can clearly see the boundaries among the unit cells. In order to avoid this drawback, here I will try to calculate the normal vector for each vertex in a unit cell for the 3D parametric surface. This means that each vertex in the same unit cell will have different normal vector. As shown here, suppose we have this quadrilateral unit cell. Suppose we want to calculate the normal vector at vertex 0, this point. We make a small deviation from point 0 to point 1, a very small movement along the u direction. This means we calculate the p0 using parametric function like this. We calculate p0 using p0fuv, but we calculate the small deviation p1 using u plus EPS. EPS is the epsilon is a very small amount, for example, 0.00001. So this very small movement along the u direction. So we get a p1. Similarly, we can move along the v direction. Here, p2, we get a p2 here. This means along the v direction, v plus EPS, we get a p2. Of course, you can make another change along the opposite direction. For example, negative u and negative v, that doesn't matter. You can move other directions. We can then use this point to calculate the normal vector at point 0 with the formula here. You see, n is normal vector equals p1 minus p0. This vector cross p2 minus p0, p2 minus p0. So this cross products gives the normal vector. The real normal vector will be normalized of this cross product. So in this way, we will get a smooth transition because each point on the unit cell will have different normal vector. So the lighting will be more uniform and smooth. Another improvement we can make is that in creating simple 3D surfaces, for each unit cell, we use 6 vertices of 2 triangles because we need 6 vertices to describe the 2 triangles to store the position, normal vector, and color map data. Here we can use indexed vertices, that is, real vertex only have 4 vertices, 1, 2, 3, 4, for each unit cell to store that data. This will save a lot of resource. So here we will use the indexed vertices to create our parametric surfaces. Here I will use the git tool to clone the source code used in the last video, and then make corresponding changes to that source code to build the project used in this video. Now, let's start Visual Studio Code directly from Windows Start menu. From here, this is the Visual Studio Code interface. Now, let's start a new terminal window and cd into code folder, and then create a new folder called wgpu 17 and cd into it. We can then clone the source code used in the last video with the command git clone wgpu 16. After this command, we leave a space and a period. This will place our source code in the current folder. So we can run this command. we can check direct. You can see all the source code is indeed in the current folder. Now we can open this folder from Visual Studio Code. Open folder, code, wgpu 17. Here contains all the source code used in the last video. Since parametric surfaces are in fact the simple surfaces in the parametric space, we actually create a simple surface in the UV space using the approach similar to the one for creating simple surfaces. The trick to creating a parametric surface is to map the simple surface in the UV space back to the x, y, z coordinate system. This mapping is controlled by the parametric equations. The resulting surface in the real-world space can be very different from the one in the parametric space. As mentioned before, our parametric surface in the parametric space can be formed by the quadrilateral mass grades. The unit grid is a quadrilateral with 4 vertices, P0, P1, P2, and P3. Now, from SRC folder, open the surface data.rs file, surface data.rs file. Here we need to add some new functions to create our parametric surface. Here we use the standard raster approach to create our parametric surface. We first define a structure. You can see parametric surface structure. This structure contains member fields to create our parametric surface. First one is the parametric function called f, and another is UV value range, U minima, U maxima, V minima, and V maxima, and UV derivations we call the segments along U and V direction, and other parameters to define aspect ratio, scale, and color map parameters. And finally, the param here is used to create our surface. Next, we set the default values for this member field of our structure. You can see here we set the default function to the torus here because this torus function needs to be defined later. This is the data range for creating this torus surface. This function we also use some parameter. The first two parameter is 1 and 0.3. This is the torus radius, and 0.3 represents the radius of the ring. Next, we create an implementation block for our parametric surface structure. It contains a new function here that is used to create the surface data. Here we call the parametric surface range. You can see here, parametric surface range. To get the range minima and maxima, this minima and maxima will be used for our color map. The parametric surface range is a function here defined parametric, see, surface range. They calculate the minima and maxima. Not here, minima and maxima values depends on the color map direction. You can see here is the input color map direction. 0 means x direction, direct equal to 1 is y direction, to 2 is z direction. So this minima and maxima depends on your color map direction. So here you can see color map direction, we use CD. Color map direction means we set the default value to 1. If the color map direction equal to x, the x direction is this CD equal to 0. If the direction equal to z, it will be equal to 2. Otherwise, will be set default direction use 1. This means y direction. Inside this for loop, we calculate the normal vector here. This just use the methods we discussed previously. You can see we define a small amount of number EPS 0.00001. So we can see if mu minus EPS or u plus EPS, we get the other vector P2. Similarly, we can define along the v direction. You can see PA is v minus EPS or v plus EPS. Next, we use this vector create use this small deviation to calculate the normal vector. You can see normal vector equals the P3 defined along v direction cross P2 is defined along a u direction. The normal vector will equals normalize these cross products. We then specify the color for our surface. Here we first set it to a pure color. You can see we let a color equals PS color. This PS is a parametric surface defined in the structure. Here we have another parameter called use color map. If it is true, we set it using color map. Otherwise, we use a pure color. So you can see we select the color map name and use this value range, minimum and maximum, and use this, the direction, CD is a different direction. We get the color map. Finally, we add the position, normal vector, and color map data to their array, like here. Here you can see we simply calculate this data for each real vertex and didn't use any quadrilateral grids because we wanted to use indexed vertices here. Next, we need to specify the indices using the unit cell. You can see inside this for loop, we first specify the 4 indexes, index 0, index 1, index 2, and index 3, using the unit cell. And then we add the index data for 6 vertices of the 2 triangles. This is a first triangle. This is index 0, index 1, and index 2. This is for the second triangle. This is index 2, index 3, and index 0. This is 2 triangles. So here we only use a unit cell for calculate the indices. And finally, our new function here returns the positions, normal vectors, and color maps, and indices. This data will be used to create our parametric surface. You can see here we specify the default the function as a torus. So right now we need to add this torus function. From SRC folder, open mathfunc.rs file. So here we need to add a torus function. Here is torus function. You can see the x, y, z is a parametric equation. This torus uses 2 parameters, parameter 0 and parameter 1. The first parameter is the radius of the torus. The second element represents the radius of the torus ring. So when you go back surface data, you will see the torus function is available right now. No error anymore here. This is the default function used in our parametric surface structure. Next, we need to modify the common.rs file. From SRC folder, open common.rs file. Here we need to replace its content with the new code. This code is basically the same as that used in the previous examples, except that here we use indexed vertices. You can see Our state structure here contains a member called index buffer. This is a new field because we use the index data in this example. That index buffer is used to store the index data. You can see our new function here contains a new field, new argument called index data. Also, in the bottom of this structure, we also define, you can see here, index buffer. Using this relation, we define index buffer using the index data here. And finally, inside the render function, we also need to set the index buffer here to the render path and call the drawIndexed method to create our parametric surface. That's the change we need to make in order to use the indexed vertices. The rest of the code is the same as that used in creating our simple 3D surfaces. 3D parametric surfaces are relatively complicated. In order to give you more time to digest the code, I will stop here for today. In next video, I will show you how to use the functions we defined today to create several 3D parametric surfaces. Thank you for watching.